Day 4. Consider the events A and B are mutually exclusive, are not mutually exclusive events. In your own words, define what it means for two of them to be mutually exclusive. So B and C have something in common. I think of the case where you roll a 4 and a 4. That's the exact same number that's rolled, and when you add those together, you get 8. So they share something in common, and that's why they're considered to be not mutually exclusive. When you look at the events of A and B, there's absolutely nothing that they have in common. Part B. Find the probability that the total is 11 or the same number is rolled. Sometimes it helps to think of a Venn diagram. So the total being 11, you could roll a 5 and a 6 and a 5. And then over here, the same number is rolled is a 1 and a 1. And all of these other examples. And so you can visually see that they don't share anything in common. When you roll 2 die, there are always 36 possible combinations. And what you see here are 1, 2, 3, 4, 5, 6, 7, 8 out of 36 ways to be satisfied with what they ask us to find. In part C, find the probability that the same number is rolled or the total is 8. We've already talked about the situation where they share 4s, but there's other 8. You could do a 3 and a 5 and a 3, a 2 and a 6, or a 6 and a 2. The same number being rolled, we've already seen, can be this way also. If we're satisfied with the same number being rolled or a total being 8, you can count how many different ways you're happy with that outcome. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 out of the 36. Just as a reminder, we call these events mutually exclusive, and these events are not mutually exclusive. So if you could make a Venn diagram and if this is considered to be not mutually exclusive. All right, take 5 seconds and read over this problem. So they give us a lot of information, and it's a good idea to put this into a table just to help us sort through all the information. So we have female students, we have male students, we have freshmen, and we have sophomores. And we know that 55 of the students are male. So I'm going to make totals. And so we have 55 here that represent male students. If there's 103 underclassmen, that tells me that we have 48 females. 31 of the students are female sophomores. And so that tells me that I have 17 freshman females. And 6 are male freshmen. So that tells me that we have 49 sophomores. Find the probability that a random student picked from this group is either a female or a sophomore. So of this, we end up having 80 sophomores and we have 48 females. But I hope that you can see that there's overlap in that we have females and we have sophomores. So that would be the 31. So this is a classic example that anytime you've got a problem that says you either want this or something else, that you have to worry about the overlap region. And you can already see that this is the formula down below, but I wanted us to understand where it comes from. So you can take the probability of choosing a female, so that would be 48 out of 103, and you would add that to the probability of choosing a sophomore. But in adding that, you've actually double counted the female sophomores because they were already added in the first 48, and so you don't need to add them again. So instead of double counting, you can subtract the part where they overlap. And so that is this formula right here. The probability of A or B occurring is always the probability of A plus the probability of B minus the probability of A and B. So there's that intersection that we talked about from the day 3 video. If events are going to be mutually exclusive, so if there is no Venn diagram that has an overlapping region, that probability of A and B occurring will be 0, which is why you could just add the two probabilities. So it's something to think about anytime you've got an OR probability. Here is a card deck, and I realize that not everybody is familiar with a card deck, but a lot of questions in math relate back to the card deck, and so anytime you can look here, you can probably find this on your phone too. Realize that face cards are not considered to be jacks, queens, or sorry, they are considered to be jacks, queens, and kings. So these are the face cards because you literally see a face on their card. So this is the sample space of a deck. What is the probability, if you're choosing one card, that you will pick a face card? So there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 cards that have faces on them out of the 52 possible. One thing I did not mention is that there are 4 suits. And these are the names of the suits. So it's hearts, diamonds, spades, and clubs. The probability of not choosing a face card, you could do this 2 different ways. You could count all of these, but that sounds like a lot. Or we've already found the probability of choosing a face card. We know that there's 100% of choosing something, and I don't care what that is, but we know that something will be chosen when I pick one card. So I can do 1 minus the probability of choosing a face card, and that gets me the probability of not having a face card. The probability of picking a king or a queen is 8 out of 52. Those are mutually exclusive events. There are no king-queen cards. And a red or black is 1. Because the probability of picking a red is 50%, the probability of picking a black is 50%. When you add those together, you get 100%. The probability of picking a 4 or a red card, those are not mutually exclusive. There is an overlapping region. So we look at the probability of choosing a 4. So there are 4 cards that are 4s out of the 52. There are 26 red cards, and there are 2 cards that are both 4 and red, so I have to take away that probability. Face card or club, so 12 out of 52. There are 13 clubs in the deck out of 52, and there are 3 cards that are face cards and also clubs. Number 3, use the sample space given above to answer the following questions about picking 2 cards without replacement. You want a face card. So that's 12 out of 52. And then you want another face card. So you are reducing the pool so that the whole pool gets reduced. But because you've already chosen a face card, the next number also gets reduced because you have fewer face cards to choose from. The probability of no face cards will be 1 minus what we just found. Sorry, that's the next part. No face cards will be 40 out of 52 times 39 out of 51. You have to guarantee that there's not a face card here and there is not a face card here. The probability of at least one face card could be 1 face card, or it could be 2 face cards. What it is not is the no face cards. So that means you can subtract the probability that we just found. Because that's exactly the same thing as doing 2 face cards plus getting 1 face card. And 1 face card is complicated because you could get a face card the first time and then not a face card on the next one. Or you could get not a face card on the first one and a face card on the second one. And when you add all three of those up, you'll get exactly the same thing as if you had just done 1 minus, no face cards. This 1 minus idea is the complement idea. And it's an important concept in probability to understand. So we're going to go through number 4. Calvin and Phoebe visit the children's ward at the hospital. The probability that Calvin will catch mumps as a result of the visit is 0.13, and the probability that Phoebe will catch mumps is 0.07. Find the probability that they both catch mumps. 0.13 times 0.07. Calvin does not catch mumps. Will be the complement. So 1 minus 0.13 is 0.87, and Phoebe does not catch mumps is the complement, so 0.93. Calvin and Phoebe both do not catch mumps. Multiplies both of their probabilities, and at least one of them catches mumps. It is 1 minus the probability of both of them of neither of them getting mumps. So that's 1 minus 0.87 times 0.93. The phrase at least 1 or at least 2 is when you know that you should be doing this complement idea. The rest of that is going to be homework, and I'd like for you guys to check your answers on Canvas.